Session 11, pretty exciting. Today what we want to do is we want to talk about aggregate properties. Up to this point we've been talking about aggregate production, shape, gradation. Today what I really want to talk a little bit about is the density properties of aggregate. I want to start going through some of the issues related to specific gravity and their internal void structure. I'm going to try to make up a little bit of time today, so I may not get through all of these slides, and then I'm going to jump on over into mixture proportioning so we don't get too far behind. One of my goals and New Year's resolutions for this year, as opposed to the last 9 years, is to actually finish all the material that's on the syllabus, and I am going to try to make sure that we get that done. So what I really want to do is I want to start off and I want to talk about two types of porosity. And these are going to be the two types that are really of most interest. We have the porosity that's going to exist between the aggregates themselves. And typically here what we're looking at is we're looking at the space between the aggregates and internal porosity. And this is going to be the pores that are actually within the aggregate itself. The space between the aggregates is going to be important because it's going to dictate the volume of paste that we have to work with. And the internal porosity is going to dictate primarily the moisture content. And the moisture content we will see coming back up at the end of the semester or middle of the semester when we start to talk about quality control issues. So these are the two types of porosity that I really want to focus in on. As we could all imagine, most of us have led a privileged enough life that we've seen a rock at some point in the history of our lives. We know that rocks are not all uniformly shaped. They are irregularly shaped, and there are going to be voids where they fit together. So I've got these yellow Purdue rocks here, these yellow Purdue aggregates, and you can see if we were to put these together, there would be space that I'm tracing out right now that would exist between those aggregates, and that space is really the type of porosity that we're talking about. That's one of the types of porosity that we're talking about. This is the paste. This is the space that needs to be filled in by paste in our concrete. It needs to be filled in by the paste and mortar inside of our concrete. And it's really where the aggregates don't fit together very well. The second type of porosity that we're really dealing with here is the porosity that's shown, and I've drawn my own very creative version of a aggregate, and inside of that aggregate I have these pores, and in this picture those pores are partially filled with water, which I've drawn here in the aqua color, and then they're partially empty. Now, this is not a very accurate description of what the water distribution actually looks like in those pores, because we would typically empty out a hole in the middle of the porosity first, because the water will like to stick to the pores. But just to give you a little bit of an illustration that there will be some water in the system and there will be some air in the system if it's not completely saturated. The other end of the spectrum that we can really be on is a case where we've got water sort of sticking to the surface of the aggregates as well as filling in all the internal porosity. So this internal porosity is really going to be a key issue for us in terms of trying to get good quality control, because believe it or not, this type of water can influence the water to cement ratio substantially. And that's going to be part of what it is that I want to talk about today. So I want to talk a little bit about, to start, I'm going to talk about this type of porosity. We're going to talk about the internal porosity of an aggregate, and we'll talk about the moisture content of these aggregates. The idea here is that a particle is going to assume space. The particles are going to assume space that's not cement. This particle is going to be a stone. It's going to be solid. It's going to be a body in that it has visible, tangible surfaces. So if you were asked to find the outer surface of the aggregate, it'd be pretty easy to find the outer edge. But it's not a complete solid. There is space inside of this aggregate, and it has its own pore structure. So just like the cement paste that we've talked about having its own pore structure, the aggregate has its own pore structure with interconnected pores that are going to be accessible to gas, liquid, but typically not large enough to suck in cement powder or other materials like that. Now, I will point out that occasionally we can talk about the aggregate absorbing some of the chemical admixtures. And in very, very large porous aggregate, you could imagine it absorbing some of the cement particles, but typically that's not what we're discussing here. We're talking really about a system that looks like what we've got on the bottom here, where it's got this dark, solid space, and then we've got some sort of connected porosity that allows liquid and gas to go through the system, but really turns away any of the larger objects like cement particles. Now, the real issue of this can be illustrated pretty quickly here. If we had a dry particle and we were to add it into a cement paste system, we would displace a certain amount of the material. So through the power or lack of animation here, I'm going to take this aggregate, which I've circled. I'm going to throw it into a vial that contains cement paste. And when I do that, the overall volume of the system is going to rise. We're going to have a rise that's equal to the external volume of the aggregate. Over time, however, that system will begin to shrink or settle down because water is going to leave this paste and it's going to start to fill in the pores inside of that aggregate. And this is really one of the big problems that we're interested in when we start to talk about moisture content of aggregates. If the aggregates are too wet, they could expel water back into the mixture. If they're too dry, they're going to suck water out of the mixture. And this can be a big problem from quality control perspectives, and we're going to talk about this a little bit more. The pores in the aggregate can imbibe water. There's typically two standards that we're interested in, ASTM C127 for the big aggregates, 128 for the small aggregates. And we are going to really start to talk about a few states of aggregate because we need to know this for determining the water to cement ratio really accurately. So there are really 4 states of aggregate that we will keep coming back to. And one of these we like because it's easy to find. Oven dry is a condition that's pretty easy to find. ASTM, believe it or not, has a definition of what oven dry is, and it's being in an oven between 24 hours plus or minus 12 hours at 105 degrees. And the basic idea here is we know that we're going to drive off all the water that's not chemically combined. All right, that's the idea, that we have a system where we have no surface moisture, we have no moisture inside of the pores. We've got a system that's been dried out to 105 degrees. What we really want for the magical state for concrete mixing is we want our aggregates in this condition right here. Now, since this is the most desirable state for us to have, it's going to be the hardest one for us to find. It's not going to be simple to get there. And the reason that this is so magical is basically what it's saying is the aggregate is inert. The aggregate doesn't want to suck up water. The aggregate doesn't want to give off water. The pores are filled, so it is saturated. The surface is dry, saturated surface dry. The coarse aggregate we're going to wipe off with an absorbent cloth. Fine aggregates we're going to detect when they start to lose cohesion between each other. But the basic idea is we have an aggregate that's happy and in equilibrium. If we get slightly below that, the aggregate's going to be in an air-dried state. It's going to want to absorb water. If we get too much water, it's not going to be saturated surface dry. We're going to start picking up water on the surface of that aggregate, and it's going to give that water back and raise the water to cement ratio of the system. Now, the real problem from a practical concreting point of view comes in that this is really easy to determine, but it's hard to do this sort of on an industrial scale. It's hard to take the day's quantity of aggregate and put it through an oven, and it's going to be expensive to do that. It's really difficult to make sure that every rock is in a saturated surface dry condition. We'll talk about some of the problems even just doing this in the lab on a very small condition. So what we need to constantly do for quality control is we need to take aggregates, no matter where they exist, and they're going to exist somewhere between completely dry and really wet, and we need to be able to correct for the amount of water that they have. We need to be able to either add in additional water that we know the aggregates would absorb or take water out of the mixing so that we know that the water to cement ratio in the paste is what we expect it to be. Because the aggregate in the aggregates can alter that water to cement ratio if we don't do this correctly. Now the one real big benefit here is if we do this with a normal concrete, all right, we worry about sort of a sloppy old concrete, not real high strength, this doesn't make a huge difference. Makes a little bit of a difference. It can be important for some quality control aspects, but it's not the most crucial thing in the world. When you start to get to very sophisticated mixes, you start to get the things like high-strength concretes, ultra-high-strength concretes, self-consolidating concretes. Properly accounting for this moisture is going to be one of the key issues that leads to something called robustness. It's really making sure that you're getting the same quality of concrete that's going out every single truck. So truck 1 is equal to truck 2 is equal to truck 3, because what you really don't want to have is you don't want to have one mix that's just a little too dry, the next mix that's a little bit too wet, because this is really going to lead to problems in the overall performance of the concrete. Okay. Testing for saturated surface dry. Basically, we're going to soak the water to a point where the aggregate's not going to take up any additional water. We want the aggregate in a state where it's not going to take water, it's not going to give water back to the system. For coarse aggregate, we would simply leave the aggregate in water to a certain point of time. It would saturate. We would then towel dry these, and we would be able to determine, once they lose their sheen, we know that they're dry on their surface, and we would be able to calculate the moisture content of those aggregates. And this is the easier one. This is pretty well spelled out in ASTM C127. It's a pretty easy standard to follow. Most people don't complain about this particular standard. Right? Occasionally there's some comments about, how much do you towel dry it, when is the sheen actually lost, but this isn't the one that really causes the big issues. The one that really is sort of a little bit trickier is the one on fine aggregate. And as you could imagine, it would be pretty difficult to take a towel out and towel dry a pile of sand. So instead of using the towel dried approach, what they will actually do is they will actually make a cone out of that sand. And when the cone test is done, if the material is wet, it's going to maintain its shape. As it dries out, the material is going to start to crumble and fall apart. And the point where it starts to crumble and fall apart really gives us an indication of where the SSD condition is. It's sort of the same philosophy as sort of building a sandcastle. So if you do get the opportunity to go on a vacation and build sandcastles on the shore, you can actually think back to this class and determine the saturated surface dry condition of the beach sand through a series of pails. One of the other things that I will point out, and I think this is incredibly important, especially as we start to get towards more marginal aggregate, as we get to mixtures that are tighter in terms of quality control, water absorption is defined typically in almost every single lab as a 24-hour number. We dump the rocks in today, we measure them tomorrow, it's a 24-hour number. However, water absorption has a time associated with it. Most absorption processes in brick, in water, or in aggregate, in cement paste, in wood, observe a behavior that is linear with the square root of time. So if you look at the x-axis here, you'll notice that this isn't just a normal x-axis. This is an x-axis that is related to the log scale, which is somewhat related to our square root of time. On the y-axis, we're talking about the total water absorbed. And one of the things that I think is interesting here is you will notice that very, very quickly there's a considerable amount of water that gets sucked into the aggregates, into some of those pores. But over the course of the rest of the time that those aggregates are being saturated, this amount of water absorption is increasing. We arbitrarily, or somewhat arbitrarily, choose a 24-hour value, and we say that this is how we're going to define things according to ASTM. But one of the things that we should be aware of is that our mixes aren't only absorbing water up to 24 hours. There's typically a lot of action going on while the system is fluid up until the time is set. And that's really where we're going to determine the water to cement ratio. So for example, if we have a mixture that sets at 6 hours, the amount of water that's been sucked up by 6 hours is really what we're interested in. Now, we don't currently make those types of distinctions. We currently just rely on 24-hour data. But in the future, I think you're going to see people getting much more sophisticated on where the water is actually coming into and out of the system. And really what we're interested in when we're determining the water to cement ratio, we're interested in determining the water to cement ratio up until the point of set. And anybody know why we're so interested in determining it up to the point of set?
So the hydration process is done.
Right. At that point, the hydration process is kicked in, and we have locked the microstructure in place. So you will hear, and we'll actually talk about this a lot more when we talk about curing, but up until the system is locked, up until it's gone from a liquid to a solid, and a few years ago I had a student who told me the transition from a liquid to a solid is a sockwood, obviously, and we've taken that from the commercials from, is it Rally's, who has the sockwood milkshake. Once we get out of the sockwood state, all right, where we've transitioned from a fluid to a solid, the structure is fixed. The porosity is fixed. And if you remember back, the only thing we cared about the water to cement ratio for was it's going to determine the solid structure. It's going to define the skeleton that we have in the overall system. And that's really what we're looking at here in terms of aggregate absorption. Right, you will notice that there will also be a lot of other aggregates that we will start using, marginal aggregates, that can absorb water over a much longer period of time. Some of the lightweight aggregates, some of the slags that we'll be talking about, some of the marginal aggregates can absorb a substantial amount of water over a long, long period of time. Right. Surface moisture is all the moisture that's going to be in the aggregates except for what's in the pores. All right, surface water is typically going to be extra water that's given back to the concrete, so it's going to increase your effective water to cement ratio. It's going to make the system more porous. Compensating for this is usually a critical in concrete operations, and I will point out a few things about this that are kind of interesting. Here is a typical bulking type plot. This is the volume of sand, the volume that sand occupies as you change the moisture content of that sand. So we go from a system that may be oven dried all the way over here. You start adding moisture into the system, and what you will see is the volume will actually increase and then decrease. And the basic idea here is you've got the particles. As you start to add water into the system, it's going to push those particles apart, and then you're going to have particles kind of swimming in water, and the system is going to start to reconsolidate. One of the things that's kind of interesting about this is there's a certain volume percentage here. We got 5% moisture content where the system is really kind of at its maximum volume. This is going to point out actually two things that I find sort of fundamentally interesting. One of these is that we are going to be, and this is probably the more practical of them, we are going to be doing our mixture proportioning based on weight. All right, there are a few procedures out there that base mixture proportioning on volume, but this is a less accurate method, and the reason it's less accurate is for exactly what we're talking about here. We can have considerable bulking of the sand. Even though it's the same mass of sand, it will be taking up a considerably larger volume based on the interaction that it has with water. So there will be a few mixing procedures that take place based on volume. Typically smaller operations will do this, but almost every other operation, and the more accurate way to go is to be doing the mixture proportioning based on mass. And one of the reasons is for this particular case right here. The other thing that I find somewhat interesting is many times, especially in the winter months, states that don't necessarily want to just cause corrosion problems constantly will, instead of using just salt on their roads, if it's too cold for salt or they want to mix it with something, they will mix it in with another material. And you guys can probably guess the other material that they will put on roads to help in the icing process is? Sand or a very, very fine stone, an anti-skid stone. In some states, it is very common to buy that anti-skid stone based on volume. So what do you think every producer does?
Adds water.
They add water. So much like a very fine sod that you put out in front of your house, you will find producers out there watering their aggregate, because if someone's buying it based on volume, they can make more money off of their aggregate by fluffing up the overall system. Okay. Aggregate moisture, there will be ways that we can actually calculate this. This is the same type of picture that I showed a little bit earlier. We've got the oven dry case. This is the easiest one to find. This is the first thing that most technicians are going to do when they show up to a plant in the morning. When I was working at the ready mix plants, the head technician would keep the little pie pans in the back of his car, and on his way in the morning he had this procedure worked out where he could grab 2 samples, keep his jelly donut and coffee, and make it in, because the first thing that he was doing was he was throwing these samples in the oven, because that was going to dictate how the mixtures were going to be batched for the course of the day. So really we're looking at the oven dry. This is going to be a very critical test that's done at the lab. All of our proportioning is going to be based off of the SSD, conditioned saturated surface dry. And the very simple ways that we can start doing some of these, we're going to define absorption capacity like it's defined in your book as the weight of the saturated surface dry minus the weight of oven dry over the weight of oven dry. So here we're really talking about the distinction between the oven dried case and the saturated surface dry case. So the case where it's really easy to start out at compared to the case where we want to be. The effective absorption is typically going to be determined for the air dry case, where we've got the saturated surface dry minus the weight of the sample over the weight of the SSD. And surface moisture, we're typically going to be talking about the wet weight minus the weight of the sample over the weight of the the wet weight minus the weight of the SSD over the weight of the SSD. All right. As I mentioned, typically these are going to be done fairly quickly. In practice, people want speedy tests to be measuring moisture, so you will see people using a variety of different types of procedures. Hot plates are fairly common. One of the places that I worked at, they would have something that looked like a short order cook was working there, although slightly messier, and they would be bringing in aggregates constantly to be determining the moisture content. There's also some groups that use the microwave test. One of the things you need to be careful of if you use the microwave test is any of your aggregates that may contain metallic components can be a little bit of a problem. Many people, there are standard tests that are out there, but many producers like speedy non-standard tests to help them get to where they need to be because they can control their process a lot faster. And many of the technicians are going to be using this to do things like adjust water. And I will show you an example of one of these that's frequently used. Here is a typical type of a moisture meter that can be placed in a plant. In a concrete plant, you're going to be frequently trying to monitor the moisture, especially the moisture of the aggregate. Somewhat convenient method that some people like, some people don't like, is a moisture meter that can actually be placed out in the system. This is a system that is very simple and easy to use. It's based on the idea of electrical current or microwave. Basically, the idea is it will tell you the moisture content by relating a change in resistance of the system or some microwave value back to some known calibration curve. Now, one of the things that I will mention, some people love this and think this is the greatest thing in the world because it gives you a number very quickly. Many plants will have these attached to them. And I can show you many plants in Indianapolis that have this lovely technology attached, and someone has gone to the side of the plant with a pair of wire snippers and cut off the wire that extends from the moisture sensor back to the plant. And one of the issues from a practical point of view of these in the field is they tend to get aggregate clumping around the sensor. So even though this may be in the bin, the aggregate will tend to clump around that and the rest of the aggregate will move past it. So it's sitting there and it's sensing the aggregate and it's doing an automatic adjustment on moisture, but it's been sensing the same aggregate for the last 3 months because it's clumped up around there. So that's one of the things that people are interested in. This is a little handheld one that James Instruments produces that you could go out and jab into your sand and get a pretty quick measurement. As mentioned, to adjust for concrete mixtures, people are going to do daily corrections. They want to determine the moisture content, simply the stockpile moisture minus the SSD over the SSD. So they could get this and do adjustments for their mixed water. If the moisture content is positive, then water is subtracted from the mixed water. If it's negative, water is going to be added to the mixed water. We will come back to this later on when we do mixture proportioning and water adjustments to make sure that we get that right. I'm going to jump in quickly into some issues of aggregate packing. We talked about this briefly last time, that if we use only mono-size aggregates, we will get a system that has a lot of porosity. The best way to reduce that porosity is to put in different aggregate gradations, and that's one of the things that we're going to really be trying to do to get the fine aggregate content, usually between about 30 and 50%. 35 and 45% is a pretty safe place to be. We went through the rules of thumb last time. One of the terms that we're going to come back to is the unit weight. Unit weight gives us a measure of this space that's between these particles. The unit weight is basically dumping a bunch of this aggregate into a bucket and weighing how much a cubic foot of this material will weigh, and that gives us an indication of particle size. Aggregate gradation, this is simply a frequency distribution of the size of aggregates that are inside of your mixture. So this is a histogram of the different size fractions of the aggregates that are within the mixture. So here you can see the sieve size being plotted along the x-axis. You will note that they are kind of weird units along the x-axis. It's not a linear axis. And then the percent retained, this is the percent that's on each one of these sieves. And these points are simply a histogram of the percentage of aggregate that's in each size range of this particular aggregate distribution. Now, apparently, one of the things that I was mesmerized by a few years ago, I looked up very quickly a paper on the history of sieve analysis. And it was just to give you guys a little bit of what would cause someone to want to do that. It was snowing. It was a Sunday afternoon, and I ran across a paper that said the history of sieve analysis, and it was like a 14-page paper, and I couldn't believe that there was 14 pages of information on how you dump rocks through a wire mesh. ASTM C136 is the standard test to use. Typically we are using wire cloth sieves today, although I will point out that this article goes back to the days where this was not standard. And I will point out that in our laboratories downstairs you will find some very weird looking sieves that apparently date back nearly to the 1920s and 1930s. That are part of this grand debate on what is the best type of sieve to be using. So they are typically wires that are interwoven. They'll be nestled together, and they'll be able to sort of sieve out the different sizes of the aggregates. Grading limits are going to be established by ASTM C33, and we'll sort of talk about this in a couple seconds. One of the things that I want to point out here is ASTM C33 is designed to accommodate all. ASTM specifications are consensus documents, which means that pretty much, although everyone in the room doesn't have to agree, almost everyone in the room has to agree or find that one person who's not agreeing non-persuasive. This means that when specifications go through ASTM, they are fairly broad so that they satisfy everyone's requirements, whether you're in Washington State, Hawaii, Louisiana, and everybody's going to have aggregates that have slightly different properties. One of the things that I will point out is just controlling your aggregate to the ASTM specs is going to be a problem for quality control down the road, and we will talk a little bit about this. Apparently the big debate and what led to this entire 14-page article on the history of sieves was in the 1920s there was a grand debate between using a sieve of wire mesh that created square holes, essentially, versus a metal plate that had round holes in these. And I found the terminology fantastically interesting. In 1928, they conducted a scientific survey of city specifications. 7 cities specifying square openings, 11 cities specifying round openings. And that apparently was the scientific study. I think it became scientific because they used some numbers. But there was apparently a grand debate between these. In the U.S., it's pretty customary today to use the wire sieves, although other industries will use the sieves with the round holes, which you'll find down in the lab. Generally, for aggregates, we are using the square openings. ASTM put its foot down in the 1930s to solve this burning debate, and we now have this, and we're ready to move forward. The biggest issue today is the idea of metric versus U.S., and you will actually see quite a bit of debate still going on in this area. Again, we're going to divide things into size fractions. The sieves are going to have square holes. larger sizes. Typically for larger size sieves, a number 4 and number 8 sieve, you're talking about the distance between the wires. Number 4 sieve, you've got 4 wires per inch. Number 8 sieve, you've got 8 wires per inch. Smaller, when you get to smaller sizes, you're talking about the number of lines per inch. Here we're talking number 100 is 100 lines per inch, something like that. The term harsh is used to describe aggregates that may be particularly excessive in one particular size range. So if you hear someone talking about an aggregate grading that's particularly harsh, that's what they're talking about, something that has a lot of one particular size grading. Now this is really what you guys paid the money for today, because this is one of the best animations I've ever created in PowerPoint. Here we see a gentleman who's very excited about running the sieve test, the ASTM C136 test. Here he's doing this on coarse aggregate, so you got a little bit of a scale of the size of the sieves. And basically what's going to happen is a large volume of this aggregate is going to be placed on the top of the shaker. We are going to then tighten this down so we hold these sieves in place. We are going to begin jiggling this. And we're going to jiggle this for several minutes, and then what we're going to do is weigh the amount of material that has been caught on each one of these sieves, and the material caught on each one of these sieves is going to be referred to as the percent retained. Now I have illustrated this in case it is difficult to understand. The largest openings on the top going all the way down to the smallest openings in pan on the bottom. I have added my aggregate to the sieve, and now is when the fun takes place. I have saved all the dust and all the noise. We have collected the different amounts of material on the different sieves, and that is going to be the weight that is retained on each one of those sieves. I will mention that there is quite a bit of interest in moving to something that gives a little bit better information, and you're seeing people now move away from sieves, or at least talking about moving away from sieves, to talk about automated video graders, lasers. There's actually a group at NIST who does X-ray on aggregates and then models them like they're little asteroids to get surface characteristics. It takes them about a day to do each rock. It's not a commercial application yet, but I think some of these things you're going to see very commercial very soon. In this particular picture here, you could imagine aggregate being dropped by a laser in a real production facility, and it would be giving you an idea what the size distribution of those aggregates are. Grading curve provides you a relative measure of the size. This is basically what's referred to as a percent passing curve. So much like the curves that I was mentioning earlier were probability distribution functions, this is a cumulative distribution function. So what does that mean for the person who hasn't been sitting through statistics class every day for the last 15 years? Essentially, the other curve is a histogram. So that's telling you what's the weight of each aggregate size. This is an integral of the histogram. This is adding up the different size fractions and counting the entire percent passing or the entire percent retained, all right, over a particular period of time. Now, ASTM provides boundaries. You can see here that ASTM C33 has an upper bound on the percent passing and a lower bound on the percent passing. Sieve size plotted along the x-axis, percent passing along the y-axis, and basically you should see your material falling somewhere in between those two lines for it to be consistent with the overall process or with the overall specification. Again, here is your typical gradation curve. Here are your typical gradation curves. So you can see that there's a little bit of flexibility here. You can and should be tightening up these specifications if you're running quality control, and we'll talk more about that when we get to this. Last class we talked about the idea of particle size. One thing that I did not talk about last class, but we will talk about here very quickly, is the idea of fineness modulus. Fineness modulus comes out of ASTM C125. Fineness modulus is an empirical measurement of the fineness of the sand. So essentially what you're going to do is do your sieve analysis. You're going to obtain the percent cumulative that's stacked up on the sieves, divide that by 100%, and you will get a number that is like 2.59 here. This is essentially like a first moment area, all right, of your distribution, of your frequency distribution. So this is an empirical measurement of what is sort of the average fineness or the average particle size of the material. Higher fineness modulus means the material is more coarse. Lower fineness modulus means that it's less coarse. Typically, the reason that we're looking at fineness modulus, if we see a change of about 0.1 in fineness modulus, you can start to detect that out in the field. Right, 0.1, 0.15, you're going to start hearing back from finishers, and that's one of the ways that people are going to be looking at this. As I mentioned, it's loosely related to a first moment analogy. It's also loosely related to the idea of surface area, so it's kind of an inverse measure of surface area. So, as mentioned, it will cause differences in finishability. Normally, we're getting numbers in the 2.5, 2.8, 3.2 range. And typically 0.1 you start to notice at 0.2 is definitely noticeable and is going to start getting calls. And I am going to jump ahead here. I'm going to skip the rest of the information here on aggregate. We will come back to quite a bit of this as we start to go through mixture proportioning, but I want to jump into at least start some of the basics of mixture proportioning so we don't fall too far behind. This is kind of a unique facility. This was designed by Corbusier in the 50s, and it's a chapel. And one of the things that's kind of interesting about this is Corbusier really liked designing in concrete because it gave him quite a bit of flexibility. He had flexibility in determining the typical volumes that he wanted to utilize. He was apparently a very short man and believed that buildings were designed with an 8-foot ceiling was just overkill, so he made much shorter facilities. But he also liked to play a little bit with the idea of volumes. And you'll remember in the 40s and 50s, architecture and building processes are changing considerably. If you look at this facility, it looks like a massive concrete structure. On this wall, actually, this wall over here, you'll see quite a few windows in this wall, and it creates sort of a fantastic light show inside. But Corbusier really used the idea of this formable concrete to really make it look a lot more massive than it actually is. Turns out that the roof on this is about 1.5 inches thick. But the way that he portrays it, it looks like a very massive structure, and he makes these walls look very, very massive, so they look back at something that's sort of a throwback in history. Mixture proportioning, we'll talk a little bit about some of the details here. There are a few things that we really need to consider. Placeability of the fresh concrete is going to be one of the vital issues. Consistency in terms of quality control. Mechanical performance of the hardened concrete. Durability of the hardened concrete. And the biggest one that we're going to be excited about is really the economy of the overall mixture. Mixture proportioning depends a lot on the application that we're using, the available materials that you've got, and the available workforce and the available equipment. Not all mixtures are going to be designed equally because every one of these things change. The materials that you have locally available, the type of equipment that you have, and the type of application are going to be very different. The economy part of this, there's going to be a cost to the materials, a cost to the labor, a cost to the equipment, and then someone someday may want to make a little bit of profit, and that's going to be thrown in there as well. The labor and the equipment is going to largely be fixed. The one thing that I will throw into this situation that really opens up the discussion is self-consolidating concrete. Because while we talk about the labor and equipment to place concrete being relatively independent of the mixture, self-consolidating concrete throws that into a whole new market. And if you have concrete that could eventually place itself with no one on site or one person on site, it really changes this equation a little bit. The real goals that most people are trying to do is they're trying to obtain the best materials that they have locally available, and they're going to be trying to minimize the binder typically. Minimizing the binder because they want to optimize the aggregates. This will be good for most mechanical properties, but it will also allow them to reduce the amount of cement that they're using and typically save money. Now, one caveat I will tell you about, and we will get to this at the bottom of the screen, there is a little bit of something that we should keep in mind from a practical point of view. And every time we start talking about mixture design and optimizing the mixture and refining the mixture for a particular application, there is a degree associated with quality control and risk. And sometimes it may be cheaper to over-design and send out an over-designed mix than to take a risk of a material failing or redesign. An example of this, if you are making a 2-foot by 2-foot patio slab for grandma in the backyard, spending a month and a half to optimize the mix, you're going to waste more materials than you're going to actually use in optimizing that particular mix. So it may be easier just to go with something that's off the shelf. So you really want to sort of keep an eye on not necessarily squeezing the nickel on every single mix, but really there's a balance between the risk associated with it, people's familiarity, and the quality control aspects of it. Has to be able to be placed and compacted with the local materials. All right, the local materials, local equipment are incredibly important. Mobility of the concrete mixture is going to be important, especially in difficult applications. And there has to be cooperation between the supplier, contractor, and engineer. Some of you will have seen that the Indianapolis Library is ringing bells in the Indianapolis Star. This is a prime case of a concrete that doesn't go into the forms very well and leaves quite a few gaps. Lack of communication between the supplier, contractor, engineer. The one rule that you should walk out, at least today, thinking, much like watered down drinks at the bar, just say no to H2O. All right? Water should not be added indiscriminately. And that's a phrase that comes from the National Ready Mix Concrete Association. The indiscriminate addition of water should not be tolerated. Translated into lingo that we all speak, don't add water. We will come back to this over and over again. There are issues with adding water. All right, we have to be willing to just say no. Few other things that I'll jump into before we get into mixture design. Durable concrete is not the same as high-strength concrete. You can make fantastic high-strength concrete that cracks like crazy or isn't durable. All right, high strength and high performance are not synonymous. Durable concrete is not synonymous with strength. Many times an increase in strength comes about because of reduction in water to cement ratio. A reduction in water to cement ratio has benefits in terms of durability, but they are not synonymous with one another. The place where this becomes the most important is it is obviously not an appropriate way to specify durability to specify strength. All right, same way if you wanted to tell someone what type of pizza you wanted, you wouldn't tell them that you had a hamburger at lunch. All right, that doesn't help them to know what type of pizza that you want for dinner. Now, you may know in your own mind that you don't want ground beef on your pizza because you had a hamburger for lunch and that's why you were telling that to them. But you need to tell them the information that you want. So if you want concrete that's resistant to freezing thawing, you have to put in a specification that is freeze-thaw dependent. If you want a concrete that's not going to undergo ASR problems, the solution is not to specify high strength. Strength is not a direct surrogate for durability, and we'll keep coming back to this. As we've mentioned before, most deterioration is related to water flowing through the material, water freezing inside of the material. This is a complex process, and we want to try to keep the process as simple as possible. Now, the authority, the group that makes the rules, is ACI, and ACI has a lovely series of committee reports. They will stack up and go about 9 1/4 inches wide on your bookshelf. There are hundreds and hundreds of committees on things that you never thought people could be excited about with concrete. Lunar concrete, different types of concrete and definitions for concrete. There are committees dedicated to this. ACI 211 is the committee that is dedicated to mixture proportioning. Now, the ACI committee that almost everyone in here is familiar with is 318, because that is the building code. There are about 400 other committees that deal with specific aspects of concrete, concrete materials, concrete specifications, concrete curing, nuclear construction, early age concrete, creep, shrinkage, other things. 211 is the one that deals with mixture proportions. This book will contain all committee reports, mixture proportioning, design procedures, and is a pretty good reference when you get out into the field, when you get out into practice. Usually someone will have a copy of this because it's pretty much, it's a very comprehensive source of information on the concrete industry. Concrete in the U.S., what we are trying to look at here is a logical system of straightforward steps that enable us to implement things based on the characteristics of the available material. All right, so what we are trying to do is a series of straightforward steps to proportion concrete. Now, I will point out here that, again, Much like ASTM, ACI is a consensus document of what everyone agrees is a good set of steps to move forward. This procedure, in my opinion, is very dated. Many producers will use something that is much more refined than the ACI procedure. I am simply going to cover this because I think it hits some of the basics that people should be aware of. ACI is the authority on mixture proportioning. All right, it is the authority that is published, but a lot of places have a lot of internal information on how to better mixture proportion concrete. All right, many commercially available programs exist, and this includes a lot of tricks of the trade, secrets of the trade, different ways to optimize grading. I personally will state this, and I hope that it does not quell any of your enthusiasm. I find 211 to be a very boring document. Following a series of steps is not what made me want to become an engineer or a scientist. I am going to try to explain the steps, but I'm going to try to give us a little bit of perspective on where the steps come from, why they're important, and what they're there to try to do. Like most good things in life, there is a lengthy list of steps. We're almost up to a 12-step process for concrete. We're up to 10 steps. I think maybe step 0 should be admitting that you've got concrete and forgiving yourself at the end for concrete or something like that. But we've got a 10-step process that we're going to work through. The first step is really assembling the information. All right, so here what I'm going to do is I'm going to go through the 10 steps. I'm going to show you the same list over and over again so you know where we are in the 10-step process. I'm going to try to explain a little bit about where the steps come from. And then I'm going to show you slides that have a lovely pale yellow background. And this lovely pale yellow background will be part of the example that I'm going to do to show you how we would actually use this. So I've tried to do it so that it goes hand in hand, and at the end we've worked through a complete example. Assembly information, workability, where is it going to be placed, what is the strength that's required, what's the durability, what's the economics, all right, how do we design this mixture to meet all these needs? Job specifications are going to be the instructions that tell us how to build our particular concrete. They're going to give us information on the specified strength. Typically, they're going to tell us things like the maximum water to cement ratio, and that'll be dictated a lot of times by the exposure condition. They will tell us things about other limitations. A frequent limitation that you will see is a minimum cement content. So, for example, if you pull up INDOT's specifications on how to make a concrete, they will tell you the minimum strength, they will tell you the maximum water to cement ratio, and they will also specify how much cement that you need to use to get there. They will tell you the volume of air that you typically have to have if it's an exposed condition, tell you the slump that they're shooting for. They'll give you information on member dimensions or aggregate size and things on reinforcing steel. They will also tell you limitations on things like supplementary materials or what time of the year supplementary materials can be used. October 15th in the state of Indiana, no one in paving operations is allowed to use fly ash anymore. All right, that's a pretty clear example of something that would be in a specification that a producer would need to know. Exposure conditions, we're going to need to know a little bit about this. This is I guess a modern version of sort of a rock monument. The Grand Rock Monument in the UK is Stonehenge. So this is a modern version of Stonehenge in the UK, where this is an exposure site to see how much salt is getting into vertical surfaces as it's splashed up from the roadway. So typically they're looking here at how much sulfate, what's the freeze thaw conditions, what's the salt. You'll also need to have a little bit of information on how well you produce concrete. What's your track record? What's the consistency of the typical concretes that you make? We'll also need to generate quite a bit of information on the material properties, specific gravities of the different materials, a bunch of properties about the aggregates that we'll talk about, and what admixtures that we're going to need to have in order to make this concrete. So for our first step, and in this class, most of this is going to be given to you. In practice, this is information that you're going to have to hunt around for. We will be looking at a reinforced concrete beam. It will have moderate exposure, and I will give you moderate exposure, although typically your specification is not going to say moderate exposure. You're going to have to determine for yourself what the exposure conditions are. Maximum aggregate size that we'll use is 1.5 inches. We'll shoot for a 28-day strength of 3,500 psi, and then I've listed all of the different material properties that we'll be using down here. So we've got the specific gravities of the materials, the densities of the materials, the dry rotted weight, fineness modulus, and the difference from a saturated surface dry condition. Second step is to determine the workability. So we will use the very fine test of the slump test. If the slump test looks like a funnel that was sawed off and concrete was dumped into it, it was. This was used when the world's largest concrete canoes were being placed. In order to control consistency in the lightweight aggregate concretes that were being used in those destroyers that we were talking about earlier, they devised a test to say how consistent the mixture was. This is what they came up with. This test has been in existence ever since. The basic idea, you'll put 3 lifts of concrete in. They will be inside of this metal funnel. You will pull off the funnel and you will measure the slump, how much the concrete sinks down. This will give an indirect measure of the workability of the concrete. It will also give a measure of the consistency of the concrete. So now that we've covered with the slump test, we can all rest easily this weekend. We will pick up from here on Monday, going through the rest of the mixture proportion.
Dip into my vodka drawer if you want me to.
I wouldn't be in there any longer than I have to be. It's embarrassing in boots.
Oh, I don't think I'm supposed to touch this.
That's no biggie. I'll just go up there and maybe start on this homework.
Rubbing alcohol if anybody asks.